You do today?
Well, it's just my size.
And apparently no paper. Once again, Kayla has disappeared from existence.
What?
Kayla has disappeared from
I don't
existence.
think she's been at any classes tonight. She knows.
So, capstone, what's capstone's workload next week? Do we have any major deliverables next week? Yeah. What?
Mostly it's waiting for stuff to get delivered. Like parts of the
Okay.
Actually,
All right. I just want to make sure that we try to work around that if possible with this exam. So here's what I'm thinking for the exam next week. We all are aware that there's an exam next week.
Yes.
Okay, so I'm thinking for the exam next week, we might do it on Thursday,
All at once.
all at once. And you would just have to schedule a time between 8 and 5 to come in and take the exam. And I would give you 3 hours to take it if you want to. I mean, it still should be a 2-hour exam,
Between 8 and 5.
between 8 and 5.
I won't be able to do that.
Really?
I
I
have.
have class all day and practice starting at 3, so
And blow practice.
it's better in theory than
Yeah.
practice.
We're talking about practice. Not a
That's
game,
right, that's right.
practice.
So we all have busy schedules on Thursday, so we have to do it Monday, Wednesday, or Wednesday and Friday then.
I can do Thursday.
I just,
I really like that.
You know
idea,
why?
Because I'm
Thursday.
flexible and a great student.
Yeah. What are you saying, Jesse?
I mean, I'd rather skip my chem lab on Thursday than have to do it Wednesday, Friday again. I like the 3-hour idea. That's a good idea.
I mean, I could see if someone could pick up ITA, UFIS
At what time?
from 1 to 3.
Okay, so what's your story from 8 to 1, man?
Which is I have lab from 8 to 10, I have an hour, and then I have class from 11 to 1, or from 11 to 12, and then I eat, and then I have,
Controls in the middle.
practice.
I should talk to Gagner about dropping controls on Thursday since he's giving you a test on Tuesday.
Actually, he was considering dropping a class.
So maybe I can convince
If you could
him
do
to
that, then that'd be
Then
fine.
I'd put that in the middle of controls. Would that free up your schedule, Jesse?
Yeah, because then I have the 10 to 1 block too. That'd be good.
Who do you
guys
eat
okay?
lunch?
I
can do it early enough.
Okay.
Anything.
I'll talk to Gagner, see if we
Start
can,
at 10:30.
see if I can do that.
5:30 me?
Oh, yeah, breakfast.
All right?
Schedules are logistics.
You can't do it at all even if we cancel controls?
No, I can do it whatever.
Does that mean we don't have strength materials next Wednesday or Friday?
That's correct.
Love that. Let's do it.
Okay. All right. I mean, we could probably get together and review or answer questions on Wednesday if you wanted to, because it'd still be before the exam. But I would not prepare any materials, we would just talk about whatever questions you
But
had.
just, you don't have to.
Let's go with that.
We'll just all come.
Break.
I mean, it's nice to
Okay,
have more than
all right,
one
let's-
ready for practice every day.
I'll talk to Gagner about that. Don't let me forget when I get out of here to go talk to him about that. Make sure that that works. Okay, 10:13. State of plane strain on an element is given. Determine the equivalent state of strain, which represents the principal strain, maximum in-plane shear strain, and the associated average normal strain. Specify the orientation of the corresponding elements for these states of strain with respect to the original element. All right, Colin, what do we do?
Free body diagram.
No.
Did I get it wrong?
Yeah, we don't need a free body. We don't need no stinking free body diagram. No, not a free body diagram.
I don't know which problem we're doing. We're doing 10:13.
We are indeed doing 10:13. So we don't need a free body diagram because it's not really they're just giving us the state of strain. So what are we gonna do for 10:13?
can we just can we just start off by drawing more circles?
All right, let's start off by drawing a more circle. Where do you want me to draw the circle?
We can start at 0. Wait, no. 300,
Can't do that some stuff.
negative 150 times 10 to the 6 is going to be our center.
Okay. What else do I need?
And then we get a radius. And the point of the radius is going to be our gamma 150 up. So positive 150, which I guess is going to be down in this case.
Okay.
And then we do the average minus where it's sigma x minus sigma y. Yeah.
So where would I've got a horizontal coordinate, I need a vertical.
So the thing is our vertical coordinate is gonna be the same spot as our center point.
So you're saying we do this?
Yeah.
What's
Because-
the formula for finding that again?
Epsilon x minus epsilon y over 2.
Epsilon x minus epsilon y over 2.
I went wrong with that.
No, because it's like x, it's like the average plus epsilon x minus epsilon y over 2. Is it gonna be negative 300?
Oh, yes,
That's good.
Right, it's sigma x. So that's our R.
And now
Is
So
our,
the coordinates were given. Sigma x and tau xy, or sigma x and gamma xy are the coordinates of the other end of the radius. The center is at the average, the other end is our sigma x and gamma xy.
is it gamma, okay, is it gamma x y or is it gamma x y over 2? Is it
Gamma xy over 2.
Oh,
Okay, and that was 100, so this should be 75 then. I was misreading it, I thought that gamma was 300, and so it was dividing by 2.
Then negative 75 is gonna be our, the other side of our radius.
All right, so the other side of the radius is up here, it's at negative 75, and Ey equals 0. Right?
How's that negative 75 up there?
Because remember,
This is positive.
this is positive,
No, it's not.
gamma over 2 is positive in this direction,
why is that?
epsilon's positive in that direction.
Is it a right-hand rules?
So that the angles are positive when they go counterclockwise.
Okay.
That make sense to everybody? And then we draw a circle of that radius. Or something approaching a circle, something emulating a circle. All right? So, there's my Moore circle. What are my principal strains and what are the maximum in-plane strain? We already found the average normal strain, we already know that.
We know our maximum gamma right off the bat is going to be 150, which is R.
It's gonna be what?
150. Is it 150 over 2?
it's gonna be
We
100
gotta
squared,
calculate R.
150 squared plus.
What's R?
Square root of 150 squared plus.
Oh, yeah, I guess. Oh, it's not 100.
Square root of,
I was thinking.
yeah, so I'm gonna write it out, sigma x, sigma. Epsilon x minus epsilon y over 2 squared plus gamma xy over 2 squared. Right, that's the expression for r. Or we can look at this and notice that this is sigma x minus sigma y divided by 2, 150, and this is 75. Where's my r? It doesn't have, they didn't give me r, they just solved directly. Oh, this is before the Moore circle. So if we're using Moore circle, even though we don't really, this is from the section of the book before we got to Moore circles. So what's that value? Square root of 150 squared plus 75 squared.
167.7.
167.7. Somebody else have 167.7?
Yeah.
Okay. Oh yeah, there it is, it was in there, 167.71. Okay, so what's gamma xy max? What's gamma xy max?
Yeah, max 167.7.
No.
Actually, it's
Times
2.70.
Times 2. That is gamma over 2. Right? All we did was found this value is 167.7, but it's still gamma over 2. To find the maximum shear stress, we have to multiply that by 2, 330, what was it, 335. This times 2, because R is gamma over 2. Right?
What makes it square? You have a gamma greater.
167, no, we have 150.
150.
Okay. Okay, but we're good? As to why that's 335?
Okay.
Okay. So now what do I need? I found part B first, apparently. What's, you want to need 2?
What's this? Principal strains will be, it's going to be 150 plus.
Right, equals, it's going to be sigma average plus or minus R. Right? So those values are going to be
17.7 for the
17.71 and minus 317.
0.71.
All right. What else do we have? Specify the orientation of the corresponding elements for these states of strain with respect to the original element. So the original element is oriented there in x, y. We have x and y. This is our thing. What's our new element going to be in the principal strain orientation? How am I going to orient my principal strain? No ideas? That's my x and y. What's my new x and y? My x prime and y prime, or x1 and y1, whatever, x1 and y2, I don't know. What are my principal coordinate, the principal axes? What are the orientation of my principal axes? So right here, I've got this. All right, when this thing is strained,
Yeah.
it looks like this. All right, that's what it looks like. I want to rotate it into its principal strain direction, so that at some angle, at that angle, I'll just draw it this way. It's going to look like this. No. It's going to look like that. Right? It's compression in one direction and
So
tension in the other.
we need
So it's going to be an orientation where I can draw it like that.
So we need to find our theta.
So we need to find our theta, right? What's our theta?
But there's no angle of shear in that.
Because when we're at the principal strains, there is no shear.
Right.
At the orientation of principal strain, there is no shear strain. Right? just like with the principal stresses, there was no shear stress
Yeah.
when we were at the principal stress angle.
We can do tan 2 theta
Okay?
is equal to,
Tan 2 theta P, I'm assuming,
yeah.
is equal to what?
To 150.
Oh, you can give me an expression so we
Yeah,
can
give
see.
the expression.
Talk about opposite over Jason.
Yeah. s-
You want,
Minus is 75 over,
So it's, I'm looking for
minus 75.
gamma xy over 2 divided by epsilon x minus epsilon y over 2, or you can give it to me without the 2's. If you look at it on the picture, if you get it from Mohr circle, right, what's my theta, where's my theta on this picture? Where's theta p?
Between R and the x-axis.
Right, this is actually 2 theta p, right? So if I take the tangent of the y component divided by the x component, right, then I'll get it. So the x component here is ex minus ey, and there's the y component is the gamma exponent. Or you can go this way, or you can just, use the equation. Get rid of the over 2's. So that's equal to 150 divided by negative 300. So theta p is the inverse tangent of negative 1/2 divided by 2. And that gives me negative 13.28 or 76.72. The negative 13.28 does what? What does negative 13.28 do to my diagram?
goes in it parallel to negative x.
Right, it moves my point up here to the smaller principal strain. And the 76.72 moves me around to the larger principal strain. You see what I'm saying?
That's 76.72 times 2, it's like.
Right, times 2 is, right. And this is 26. Okay, does everybody, that make sense on the Mohr circle? So all I'm trying to do is get to here or get to over there. So I gotta solve for this angle or that angle. And either way, this angle, the tangent of this angle, is opposite the 150, or 75 in this case, divided by the x minus ey over 2. Okay? All right, and then so if I drew that, I would end up with something that looks like this. And then how would I draw how would I draw my box? If I want to draw it like this, so the extension is in my x and the compression is in my y. Yes?
This might be kind of a weird question, but why is that 2 in the tangent of theta p? Why can't we just find theta p?
That's from the trig reduction of the nominal, the any theta, or reorientation of the, what's the word I'm looking for? Oh my goodness. Transformation, the strain transformation equation. Right, where we had the cosine 2 theta and the sine 2 theta, right? Because we used the trig identity to get to that simplification. So in order to use the trig identity and simplify it, we had to go to 2 theta. That's why the 2 theta is stuck in there. Okay. Okay, so if I want it to look like this in the x and y, where am I going to draw my x?
76 degrees.
Right. So my box is going to look like so that it can be strained like that. And this angle then is 76.7 degrees.
And then if we want the minimum values, it'd be 13.28 degrees below
Right, so I could also have done it, I could draw the same box. Like this, but now this is my, let's see, is that 13.6 degrees? Yeah, then it looks like this. Right, and if I've done it well, this dash box and that dash box have the same shape. They're just anchored at different corners. Right, it's longer in this direction and shorter in this direction. See what I'm saying?
Oh, because it flips.
Right, 'cause now my x-axis,
Yeah.
I've chosen to be the compressive axis. Here, my x-axis, I've chosen to be my tensile axis. But the shape of the box is the same in both cases if I only draw my angles exactly this, at exactly 13 and 76.
Can you label on the bottom one where your 13-degree angle is?
So negative 13.3 or positive 76.7.
Yeah, I guess I'm still not seeing why I know you explained it, but I'm still not seeing why the dotted line wouldn't be shifted like out to the right.
Because if I go negative, then that makes my x component the large compressive stress. Right, if I move by minus 13, because clockwise is negative angle. So I move this by negative 26.6 degrees. And I get out here, that means I'm taking my x coordinate, this was my epsilon x. Move my epsilon x to the point of maximum compression. So now my x coordinate is going to move down to this point, which is the maximum compression.
Okay.
And similarly then, my y component on the other side has rotated to my maximum tensile strain. So now my y component is extended. Okay. But again, you see that this dash box and that dash box are nominally the same. Okay. Last thing we need is we need to know, when does this occur? Where does that occur? What orientation does that occur? Certainly neither of these, there's no shear strain in either one of them. Right, the box is not deformed at all.
It would be, the equation's tangent 2 theta s equals negative epsilon x minus epsilon y over dmxy.
Or,
Add 45 degrees.
or just add 45 degrees, because remember they're always in
Okay.
between. Right, so the maximum strain curve, then 45 degrees is 32, 31.7. So, right, so that now becomes, and it is, ooh, okay, let's see. What angle did I choose? I chose a positive angle, 45 degrees. Right, I rotated this by positive 45 over to that one. So that's going 90 degrees beyond this. Everybody see that? So that angle that I'm indicating there is a movement of 60 to 63.5 degrees from here, which is vertical. Right? This is 90 and this is 30, so right up here. Is that right? 62? No, I take that back. I rotated it, that's a negative value. Whew. Negative value 62, so that takes me down to the bottom. See what I'm saying? I rotated a negative, or rotated a positive angle, which means this moves here. This thing is 63.4 degrees. So it takes me down here. So that the shear in my x direction, my new x direction, is tensile. That's not what they drew here. Interesting. That's interesting. So it should be, well, anyway, that's the orientation. I need to, the angle at this point then is going to be like that. So this is gamma xy over 2, and this is gamma xy over 2. But I think it should be longer, and they're saying it's shorter. I've got that backwards in my mind. Point is, they only went the angle, so. Okay. Everybody, okay, at least finding theta S, even if we didn't have to, even if I can't draw the picture very well. Yeah?
Okay, I don't know if you said it there, but why is it that we subtract 45 in this case, like going from 76.7 down to 31.7 instead of the addition?
I could have added. I took this one and I added 45 degrees to it. Or I took this one and I subtracted 45 degrees from it. 6 of one doesn't the other.
Oh, okay.
Right? And it actually should be compressive, right? It should be a smaller thing. Because when I'm here, both the x and the y components of strain are compressive. So it should be, the box should fit inside the other box. Okay. You look like you're still maybe thinking about it a little bit.
Yeah, I'm fine, I'm just thinking it through.
Okay. Shall we try another? Okay. Next one is solve problem 10.4 using a Moore circle. If only we had 10.4. Oh look, there's 10.4. Okay, so let's solve 10.4 using a Moore circle. Okay, where do we start?
Free body diagram.
No, not a free body diagram.
Draw the axes of the Moore
We already have our strains given to us. We don't have to figure them out.
It's time for Moore circle.
More circle time.
It's that time of day when you can say, give me a Moore circle.
I don't think that's a song.
Wow, that's
That's pretty impressive though.
quite melodious.
The,
Melodious.
that's actually the
665
theme song
movies.
from the 70s or 80s Bush beer commercials, what that's from, that music.
That's awesome.
Anyway.
Awesome.
And
665.
you watch football all day, on Sunday, you know, you get all the beer commercials. What's that?
Maybe you should join the side.
665, something about 665.
Something.
That was one step away from trouble there. Whew. That was close.
Ooh,
Okay.
I was getting scared there for a second.
All right, what else? So I notated 665.
650 over 2 is our lot.
650 over 2 is our y position. So what would be 325?
I got a quick question. Is that an actual thing, or is it just a superstition?
What's that?
666.
It's not in the Bible. The 666 came from, I think, the way I understand it is 6 is in numerology of the Bible, if that's a legitimate thing or not. The number of man, and 3 is the number of God. So 666 is man becoming God. So that's where the 666, that's where I've heard the 666 came from. So man trying to become God.
6 is 1 less than 7. And you said 3 was the number of God.
3 is the number, yeah, the trinity.
Oh, what about 7? What's
Yeah.
7?
7 is the perfect number.
What'd you say?
Seven's supposed to
Mr. Biblical answer earlier.
Yeah,
Tell us,
yeah,
like,
7's the number of completion. 3 is God, the Trinity of God. So I know, so 666 is the number, is the idea of man trying to become God.
It's
But,
also King Solomon's income and talents each year.
Income in what? Talents of gold?
Yearly,
Could be.
it is.
All right.
get that video.
Anyway, has nothing to do with more circles. And this is all on video, so now people are like, what are they doing, man?
1035 is our,
Deadbeats. Anyway, go ahead.
1035 is our exposition.
Exposition is 1035.
Well, that's what I calculated. It's 665 plus, oh, I forgot to divide by 2.
I
bet it's gonna be 850. There's our 850, right, which is our epsilon x, right? Okay, so we know our center point, and we know the end of our radius. And so now, if we wanted to, we could draw a circle, at least geometrically anyway, we could draw a circle. If only my marker didn't run out. Okay, something like that. Good?
That might be the best one yet.
I try. All right. So now we gotta find principal strains, principal stress, or principal strains, maximum shear strain, and orientation. So what do we wanna do first?
Well, go ahead and find our principal strain.
Principal strain, tau xy in plane max equals. Doing it with the Moore circle, so we can just look up here, hopefully find it pretty quickly.
Yeah, that's like
Okay, how am I gonna find that?
strain's epsilon, right? That's sorry.
Normal strain is epsilon,
And then
shear strain is gamma xy.
Okay.
So we're finding you said maximum strain, which is used as opposed to principal strain. Principal strain is epsilon 1, epsilon 2. Maximum strain is typically referred to for the gamma.
Okay, and our principal strain is gonna be 655 plus R.
665 plus R. But we gotta find R, because the sigma max is equal to R technically times 2, but anyway.
R is 910.013.
So equals the square root of 185 squared plus 325 squared. Well, that's really not, I did not do a very good job of scaling that circle, did I?
That is not what I actually know.
So this distance here, right, is 185.
Right.
This distance here is 325.
373.97.
373.97, so 374. Times 2. Times 2,
747.
747. So they're going to show me a 747 on here. 748.
Never agrees.
748. We round to one's place. Okay.
Sometimes you round and sometimes you don't.
748. So that's just what they have in here. So this dimension is 748. Okay, so now what? So we found sigma max, or I'm sorry, gamma max.
Our principal strains are gonna be 665 plus or minus R. Or plus or minus, I think it came out to be 373.97.
So that's equal to 665 plus or minus,
The positive side in whole numbers is
I'm sorry, that's not 348, that's not 748.
1,039.
374, and that's, what is it now?
1,039 and 291.
1,039 and 291. 10th to the minus 6. Okay. So we now have our max, our coordinates, now what are we looking for? Looking for theta P. What's the angle? Again, let's use the Moore circle, let's not use an equation, let's use the Moore circle. What's the angle?
Angle is inverse tangent 2 times inverse tangent of, I think that was, so it's going to be 325 over 180 something. 185.
So it's half of that, it's not 2 times half.
Sorry.
And that gives me values of theta P of
30.18.
and what would be the other one?
Plus 90.
All right, plus 90, so 120.8 degrees. Okay? And we did that because we know this is 2 theta B. That's where the 30.18 came from, yeah.
Sorry, just as a review, can you, what's the theta difference between theta P and theta S? Like, what are the significance of those two values? Theta P is the maximum,
Theta P goes with these.
okay.
Principal, P for principal stress, or principal strain. So
So,
theta S goes over here, because the S is for shear,
oh,
the angle of the maximum shear.
okay.
On the graph, on the diagram, this is 2 theta P, this is 2 theta S, right? Because this is the point where we have maximum shear,
Okay.
the vertical line, horizontal line gives me principles. Okay. So again, once you've drawn the diagram, you should be able to figure out all the pieces you need just from looking at this diagram. Okay, so you don't need the equation, you don't need to remember the equations, you just need to remember how to construct the diagram, and then you can just pull all the values. As long as you understand that that's 2 theta P, that's 2 theta S, that's epsilon 1, that's epsilon 2, that's tau max, or gamma max. Okay? All right. And then theta S?
Theta P plus 45.
Theta P plus 45? So that's 75.18, or
1.
you'd say, or 30 minus 45.
Or, yeah.
Okay. Minus 14.82 degrees. This is the minus 14.82 degrees. I know I haven't drawn it right because I told you my scale was off. So in reality, 2 theta P is 30, this should be 60 degrees, so that I don't have to go minus 15 to get the theta S. Make sense to everybody? Cool, we're cruising. We might be able to get the third problem done. Who knows? Only the shadow knows. Okay,
We got a second problem then.
if only the camera would actually pan far enough over to film. Oh.
Today's been an interesting day for the camera.
All right, 1022, the strain at point A on the bracket. Oh man, this is not what I wanted. Nuts. All right.
Oh darn.
That's all right. The strain at point A on the bracket has components EX equals 300, EY equals 550, gamma XY equals minus 650. What are the principal strains at A in the XY plane? And the maximum shear strain in the XY plane and the absolute maximum shear strain? Nope. Do an extra thing there at the end, absolute maximum shear strain. What's that about?
That's the absolute value of maximum shear strain.
Nope.
He's couldn't,
Or is that our epsilon, or
just in case the shear strain is in the negative direction.
Nope. Let's draw the pictures.
just
Let's
our
draw the
largest
pictures.
strain value?
What's that?
Our largest strain value?
Let's draw the pictures. Let's find out.
I've got a quick question.
Yeah?
Um,
In an effort to kind of keep us from actually getting to part C, go ahead.
yes. Does epsilon z affect us at all? Or are they just kind of throwing that in as little like,
So,
it's like,
it
epsilon
all
z.
relates to part C. All
Okay.
relates to part C.
Okay.
Let's draw a picture.
Something new.
They're effectively stating, hey, this is plane strain,
Yeah.
right? EZ equals 0. Okay. Okay. Go ahead, what do we do? Principal strains in the, at A in the XY plane. What am I gonna do?
So build more.
We should be able to, yeah, we should be able to do this quickly. Where's my center?
Our center is gonna be 300 plus 550 over 2, which is 850 divided by 2, which is 425.
425. Where's my other end of my radius?
425 plus, oh, it's gonna be negative 25 over 2, so it's gonna be negative 112.5.
No.
Negative 325?
So we start off at negative 325, which is where?
Oh, negative 125.
We start off at negative 325. That's where my gamma is. My gamma is minus 650, so gamma over 2 is minus 325. So that's my horizontal, that's my y coordinate, if you will. Where's my x coordinate?
So you add negative,
No, you don't add anything. Look at this.
300 minus 550. So 2.
Where am I drawing my vertical dashed line? At 300, yes, thank you.
I was gonna say 425 minus 125, but I said
Okay, there is the other end of my radius in x. Right? So now I have my circle, and I can do, well, let's see, I better figure this out. So I draw the circle correctly. Okay, not a great circle, but again, it does the trick. So now we should be able to figure out everything if we properly understand our circle. Yes?
Is the radius always drawn with the epsilon x value in the, just the intersection of the point, epsilon x and then gamma x y over 2?
Yeah, typically, because if you've got a member, and if you've got this little chunk of stuff, this is x and this is y, I want to know how to orient it. I'm going to do it with respect to x.
Got it.
Okay. Okay, so again, the convention. It's not a mathematical necessity, it's just a convention. So, what do? So what else do I get?
Well,
Find the principal strains.
our principal strains are gonna be,
Principal strains are equal to what?
would be our average
Right.
plus or minus r, where r is the square root of 325 squared plus 125 squared.
What's R? See if it listed at 348.2. Okay, so we have 425 plus or minus 348.2. So those values are 773 and 76.8. So 773 out here, 76.8 in here. Maximum shear strain is what?
Is our r.
Times 2. 696. What is our absolute maximum shear strain?
Absolute maximum.
Yeah.
696.
Nope.
But this, we draw the three circles.
This is where we draw the three circles. There's also a strain condition between Y and Z. Right? There's gonna be a little more circle in there, because this principal strain is not 0, 76.8. Right, so when we reorient, by minus whatever that is, to get it back to the principal axes. I have some kind, my box now looks like, my reoriented box, instead of looking like this, now looks something like this. Right, I've reoriented it to get the principal planes. So now I have an X and a Y. I'm drawing in the stresses, the strains in each direction, right? But then there's also 0 in the Z. So if I took a slice through the thing at this angle, the YZ plane, I would have this circle. So the absolute max is that circle. Right? So the absolute max is equal to sigma x, sigma. Epsilon x, oh my goodness, I can't even draw. Epsilon x divided by 2, right, which is half the radius of the big circle. Right, that gives me this, or half the diameter of the big circle, rather. Right, epsilon x divided by 2, times 2, because this is gamma over 2. So the absolute max is just epsilon x, or epsilon 1, not epsilon x, epsilon 1. Right, that point over there. Right, this was epsilon 1, this was epsilon 2, and this essentially 0 becomes epsilon 3, the epsilon of the third axis. Right, everybody with me? So the absolute max is just epsilon 1 divided by 2 times 2, which is epsilon 1, which is 773 times 10 to the minus 6. Good? And right on time. Although we did start a couple minutes late, so, I could have really been. That's great, Clayton.
Not amused.
Aren't you glad that we didn't have our extra prospective student, because he would have just been freaked out by all our
Shenanigans?
Or it would have been really good.
Say that word one more time.
I'm just glad you didn't come to our modern lab, Clayton.
What?
I'm just glad you didn't come to our modern lab.
Oh, goodness.
What were you guys doing in the modern lab?
Clayton's weird.
Don't wait till I turn off the video.